absolute value functions is the last special transformation that we're going to do. So we've done reciprocals of any function. We've done square roots of any function. And so now, what would happen if we put any function inside absolute value bars? Well, first a recap of what does an absolute value bar do. If you do an absolute value bar, absolute value of a positive number, what do you get? It stays the same. And if you do the absolute value of a negative number, it becomes 7. Now, absolute value bars are really a mathematical notation for distance. And it's really asking, how far away is 8 from 0? Oh, it's 8 units away. But when we get to negative 7, how far is negative 7 away from 0? It's 7 units away. But mathematically, over time, we just get used to the idea that a negative value in the absolute value just becomes positive. So when we have an absolute value function, wherever our y values are negative, in fact, this will change all y values to be positive. And so we're going to look, what does that mean graphically? So our first example is an example that we did in our transformations unit. We want to graph y equals the absolute value of f of x, so that's asking us to graph y equals the absolute value of 2x plus 3. But now we're going to look at it from a different perspective, and we're going to use a technique for graphing all absolute value functions. Our new technique, we're going to graph f of x first, and label all of our x-intercepts. After graphing f of x first, wherever the y values are negative and they become positive, what that does graphically is it reflects it over the x-axis. So I'm going to write reflect negative y values over the x-axis. So let's see what this looks like. I'm going to start by graphing f of x first. So what is f of x? F of x is a line, 2x plus 3. It has a y-intercept at 0, 3. It has a slope of 2, so we could go up 2 over 1 and have the point 1, 5, down 2 over 1 and have the point negative 1, 1, down 2 again over 1, and we would have the point negative 2, negative 1. I'll do one more. We would have the point negative 3, 3. If we wanted to label our x-intercept, obviously this makes a straight line, but to label our x-intercept, how do we find an x-intercept? We set y equal to 0. So negative 1.5, 0 is our x-intercept. Now I labeled a lot of points on our graph. So we've graphed f of x first. This green graph here is y equals 2x plus 3. All the absolute value does is say, where are our y values negative? We can highlight those. Our y values are negative here. And wherever our y values are negative, we can reflect those over the x-axis. So what will that look like? Well, I'll redraw my graph. And wherever my graph was positive before, so at 0, 3, I'm going to label my x-intercept. We had negative 1, 1, 1, 5. This part of my graph stays the same because all my y values are positive, so the absolute value will not affect them whatsoever. But this part of my graph, which we've highlighted in green, instead of having negative 2, negative 1, I'm going to have negative 2, positive 1. And instead of negative 3, negative 3, oops, that's a little bit high, I'm going to have negative 3, positive 3. And this part of my graph gets reflected over the x-axis. And what we just graphed was the absolute value of 2x plus 3. Now, we took a long time to do that, but can you see that this is relatively easy? You can graph your line y equals 2x plus 3 quickly, and all we had to do is take that negative part and flip it over the x-axis, and we've got our new graph. Now, if we think back to February, okay, in February we started transformations. In our transformations unit, so this is the old way, you could have been asked to graph y equals 2x plus 3. What's your parent function? Your parent function is the absolute value of x. So what are some points that we have on our absolute value of x? You would have 0, 0, 1, 1. Maybe you would choose 2, 2 in this case, and negative 2, 2. Because when I go here, I see that 2, it's inside my function. What is that going to do? It's going to multiply my x values by a half. So I might choose 2, 2 because I'm already thinking I have to multiply my x values by a half. What would that plus 3 do? Well, you might be tempted to say 3 to the left. Why isn't it 3 to the left? Well, it's inside the absolute value, so it should be, but it's not in factored form. So we would have to first rewrite this as 2 factored out x plus 3 halves. And then we're going to take this graph, and our technique before would have said, okay, I'll take my points, I will do my stretches and compressions first, and I have a horizontal compression. And then I'll do my translations, and now my translation is 1.5 to the left, and so I will get negative 3 halves, comma 0, negative 0.5, comma 2, and negative 2.5, comma 2. Label those points. And you get the exact same graph, but I think in this case, the transformations unit is harder because you have to remember to factor, and then once you factor, you have a translation that is a fraction, which isn't hard, just more chances for mistakes, takes a little bit longer every time you're working with fractions. But the graph that we got there is the exact same graph that we have here. But I think it's easier with the absolute value to graph the inside function first and reflect the part over. So now that we have these steps, our f of x function, this can be any function that we've had so far this year, any graph whatsoever. And all you need to do is draw that graph first and then reflect over the x-axis. So the next example, and I've drawn the graph, the original graph for us, is a graph from chapter 1, graphing a polynomial. So if I had f of x equals x times x plus 3 times x minus 2, I've given you the graph, but we're going to take some time to say, if I didn't give you the graph, how would you go about graphing this? And first of all, thank you very much that it's already factored. Because if it wasn't factored, first of all, you would have to factor it. And you might notice that this is an x cubed graph. And from chapter 1, graphing an x cubed graph, a positive x cubed graph, we know that the end behavior acts like a line. So when we look at this graph that's given to us, sure enough, it starts down there, ends up here. That's something we know about x cubed graphs. Once it's factored, factoring it helps us find all of our x-intercepts. So from the first factor, which is x, we have an x-intercept at 0. Our second factor, x plus 3, we have an x-intercept that's at negative 3. And x minus 2 tells us that we have an x-intercept at 2. And from chapter 1, knowing the end behavior and knowing the x-intercepts is enough for us to sketch this. Once we've graphed our original function, to graph the absolute value, we just need to note, where is our original function negative? Or where are our y values negative? Those are the only parts where they're negative. So when I go to graph the absolute value of f of x, the positive parts here, they're going to stay the same. Where my y values are positive, my graph is going to stay the same. Where my y values are negative, I need to reflect them over the x-axis. And so the blue graph is the graph of the absolute value of f of x. And all that's happened is the part below the x-axis is reflected up. So any absolute value of any function is just a reflection over the x-axis. The next thing that happens is they add some transformations to absolute value functions. So let's do this example. We have y equals the absolute value of x minus 2, and then we're going to subtract 3 afterwards. So that subtracting 3 afterwards is a transformation. That's going to move whatever graph this is going to get moved down 3 units afterwards. So what I'm going to do is I am going to first graph this. And if I'm going to graph an absolute value function, that means graph the inside first, and whatever is below the x-axis will get reflected up. What does the square root of x minus 2 look like? That's a square root graph moved down 2 units, right? So if I take my square root graph and move it down 2 units, I'm going to get 0, negative 2, 1, negative 1. 4, 0, 9, 1. So because we know of our transformations unit, I can just take that square root graph and move it down 2 units. So I thought about my original points on my square root graph, right? 4, 2, move down 4, 0. Square root of 9 is 9 comma 3. Move down 2 units. Oh, that would have been over here. 9 comma 1. What does the absolute value do? That takes whatever's negative, and I'll draw it on the same graph here in a different color. 0 comma 2, 1 comma positive 1. This part here is reflected up. This part stays the same. So the green graph here is the absolute value of x minus 2. The blue graph is the absolute value of the square root of x minus 2. After we first graphed that, we can then translate 3 units down to graph what we were originally asked to graph. So I think of the points that I've drawn. 0, 2, 1, 1, 4, 0, 9, 1. I'm just going to shift everything 3 units down. So 0, 2 will now be at 0, negative 1. 1, 1 will now be at 1, negative 2. 4, 0 will now be at 4, negative 3. And 9, 1 will now be 9, negative 2. The shape, though, will stay the same as we have above. And we've now graphed our final function. The reason I wanted to show you this one is sometimes students, whenever they see the absolute value, they get stuck on positive thoughts. Now, not that I want you thinking negatively, but you're thinking so positively that you can't handle this minus 3 at the end. You're like, I can't have anything negative. That's true for just this part, right? That's our blue graph. Our blue graph has nothing negative. But if you take something and translate it 3 down afterwards, as you can see in this graph, we can have parts of that graph be negative, because that minus 3 happened afterwards. Okay, but I've seen this graph get smushed. It's like, you need to move it down 3. Oh, you can't go into the negatives. They just smush it onto the x-axis and try to graph it. No, it can go negative because that minus 3 happens afterwards. So it's a good example to see prior to your exam so you don't feel like, oh, I can't have any of my graph be negative. One for you to try. Graph y equals the absolute value of x minus 2 squared minus 4 plus 1.